All right. Yeah. So I'm going to talk about a couple of new methods we're developing for oxidized mercury. I think most people on this session have met Trevor and I now, and Tanner Allen's another student working on the project, and it's a collaborative project with May Augustin and her group. So I first want to say that we feel like, I feel like we know that there's some limitations with current instrumentation for atmospheric mercury, and we need to move beyond that, figure out what those are and how to get through them. And then also we feel like there's a need for brand new instrumentation to really look at mercury in the atmosphere in a new way. And we're trying to kind of get at both of those problems. And one way is with a field deployable calibrator that can give oxidized mercury compounds or generate oxidized mercury compounds in the gas phase to test current instrumentation and new instrumentation. And then the other side of what we're doing is a GCMS and cryofocusing system to identify and quantify ambient mercury compounds. And they kind of fit together, and I'll show you. I'm going to talk a little bit about the first one and then more about the second one. For calibration, we're using permeation tubes, and Eric talked about some of the positives and negatives of that yesterday. But I just wanted to point out that a lot of people have done this, have successfully used permeation tubes for oxidized mercury compounds in the lab and in the field, and there's a couple more field studies that are in preparation, should be published soon. The advantage of a permeation tube is it's easy and you can have confidence in what you're emitting. So if you put mercury bromide in a perm tube, you're not going to get mercury oxide out, hopefully. And so it's easy to know what's going into it. And then also, because it's all gas-based, if you can control your flow well, if you can control your temperature well, then you're 90% of the way there. I think the major disadvantage is that the permeation rate can be unstable. And this can be gradual changes or really quick changes sometimes. And I think some of that has to do with kind of long-term, the permeation tube wearing out or whatever. A lot of the instability that we've seen, I guess a hypothesis we have is that just by increasing the permeation tube temperature, then you get a lot more stability. As Eric talked about yesterday, oxidized mercury compounds are really reactive, really sticky, and getting the temperature up to 150 C or higher and using a really inert surface can solve a lot of instability problems. And so we're kind of digging on that, and May's group is digging into that too. And so I think we're getting at that. But even if the permeation rate is unstable, we still think we can get around that and provide verifiable emissions with a permeation tube. This is my conceptualization. The system is not built. Most of the parts are purchased. I'll show you it's really just a build off of what we're already doing and already have tested for the GCMS system, but the box is still just an animation. But that's the idea, is that it sits there, and just like an ozone calibrator, it dumps oxidized mercury into a Tecran system or whatever system on demand in an automated way. And this is what it does/will look like. First, what we wanted to make sure that we could do is we use LabVIEW and can integrate what's coming out of the Tecran and even send commands to the Tecran and to the calibrator together. So they each know what each other is doing. The system is conceptually pretty simple. So the permeation oven, the idea is that there's several permeation tubes inside. So you can calibrate for several mercury compounds together or separately. And I think that one of those should be elemental mercury as well. So there's an external standard, calibration standard for elemental mercury too. And then the multi-port valve just allows you to select which one you want and when. Then a secondary valve either allows the mercury compounds to go through a heated line into the Tecran, and this is literally how I think we're thinking right now anyway we want to do it, is a small line that just kind of noses into the Tecran inlet, because there's evidence that the Tecran inlet loses a lot of oxidized mercury. And so if we're injecting after the inlet somewhere up here, then that's not going to be a realistic picture of the percent recovery for the instrument. Alternatively, the valve can move and go through a pyrolyzer first, and this has been done in a manual way. We're just automating it. And then the idea is that that's a way to verify the permeation rate of oxidized mercury. There's other ways to do it, and this is problematic because then you're just turning it into elemental mercury, and then you have to assume that your system does elemental mercury right. But there really isn't another very good way, at least in to quickly and repeatedly verify a permeation rate. Other methods are a lot more intensive, and it is possible to be really to have a good idea of how good your elemental mercury recovery is with saturated vapor injections. And so the idea is then we'd use elemental mercury as kind of the primary standard for these permeation tubes. And so far in field tests, that's worked out okay, I think. Okay, so then the question is, that people ask me and I ask myself is, so we don't know what oxidized mercury compounds are in ambient air, so how do we know what permeation tubes to make and to put in the system? And the answer is we don't right now, and so we'll just try it with what we know works and see where we go. But that's the whole point of the second half, which is a GCMS system to identify mercury compounds. So I'm going to start with a very conceptual idea of how it works, and then I'll show you a deeper diagram and then some pictures. And so the idea, and this part of it is more happening at UNR, is you have an inert collection surface. I'm not identifying it because there's several that we're working on. So just whatever one we decide works the best is what that collection surface will be. And my little dots down here are mercury molecules or atoms in the atmosphere. So the gray ones are elemental mercury. And the idea is the colored ones are oxidized mercury and maybe different kinds of oxidized mercury. Okay, so then we just suck through the collection surface. Of course, we don't care about the elemental mercury for this project. We're focused on oxidized mercury. Then you put that into this lab setup, and you heat the sample collection material, whether it's a denuder or whatever, and pass it into a cryogenically cooled trap. We're heating it at a low enough temperature that the oxidized mercury compounds, at least the ones we know about, won't decompose. They'll just pass into the gas phase and then be pre-concentrated here. And 0 degrees C is the temperature we're using right now. We're still doing some tests there. You have to have a cryogenically cooled trap. You have to focus those compounds together because when they come off the collection surface, they're not coming off all at once. And so you'd get this kind of bleed out into the GCMS and have no signal. And so this step is critical to being able to see the compounds on the GCMS. And then, of course, just the GCMS, this is how you inject on the GCMS. Just heat up the sample trap. So each compound comes off separately in the GC and then is analyzed as an individual compound in the mass spec. As far as I know, so originally we started this in Washington at UW-Bothell, and we found someone had done a little bit with mercury chloride in Butte, Montana, I think. I can't remember what the university is there. University of Montana, probably. And they were able to see mercury chloride through a GCMS, but they did just a little bit, and it was acetone injection, if I remember right. We got some funding from EPRI and did that, kind of repeated that, and used some other compounds at the University of Washington. But this is the first time where we were actually doing it all in the gas phase. And the problem with the liquid phase is mercury compounds are really sticky, and you can't heat up acetone to 160 or 180 degrees. It really needs to be all gas phase without any liquid handling so that the compounds can stay intact and not get lost. So that was the concept, and this is kind of a deeper how it looks. So just like I showed with the calibrator, there's a permeation oven and a multi-port valve that allows you to select what compound you want. We've added a sample desorption oven so we can take different sizes, shapes, and types of samples and heat them through. And then that valve either passes them to a pyrolyzer, just like on the calibrator, to a vent, or to the cryogenic concentrator, and then in the GCMS. And I forgot to mention, so the whole system, at least the wetted parts of the system, right now we're keeping them at about 200 C. That seems to work better. 200, maybe we'll go as high as 220 C. We're still looking at that. And then the whole system is inertized stainless steel. So stainless steel coated with deactivated fused silica. And Techran has used that for some of their products, and Bob Talbot was talking about that yesterday. When you heat up Teflon more than 100 C or so, then it's really hard to get good seals on it, and it becomes more permeable. And this surface, I guess, the deactivated fused silica surface, is at least as inert as Teflon for oxidized mercury, and does really great. This is what it looks like in our lab. The GCMS is a Shimadzu 2010 Ultra, which, at least according to the salesman, is 3 times more sensitive than the common Agilent GCMS. So it's the most sensitive commercial MS on the market. And and I think that's helping us get where we want to go. The backside of it, so you can just see most of these ovens we bought on eBay, to be honest, and so there's the perm oven, the cryotrap oven, the sample oven, the pyrolyzer, that's what the system looks like, just in case you're curious. And it works, at least for permeated compounds right now. So this is a chromatograph of HCBr2. We injected HCBr2, or permeated onto the cryotrap and then injected. We see elemental mercury. It shouldn't be being collected at 0 degrees C on the cryotrap, so it must be decomposition of HCBr2 maybe when we're desorbing the cryotrap. But the peaks, there's kind of an ugly tail at the end, but it looks like a peak even, which we weren't sure we were going to get. And I'll show you, actually I'm going to come forward. So that's the same chromatogram, and then this is what we were getting. We've really only been running this for about 2.5, 3 months. And at first it was kind of an ugly, lumpy hill. And with some optimization of the temperatures and the sensitivity and the cryotrap temperatures and some other things too, then we're getting to where it looks more like an organic compound chromatogram. And so we're getting more and more confidence that this system actually works for oxidized mercury compounds. We're not stretching it too far. And we are certain that it's HCBr2 we're seeing and not something else. You can, if you're not familiar with the mass spectra, so on the x-axis, then this is basically the mass. It's the mass-to-charge ratio, but most of the charge is 1, and so it's essentially the mass of the atom or molecule that hits into the detector horn or detector plate. So when we have an HCBr2 peak, we see an elemental mercury grouping of peaks. So there are 6 abundant stable isotopes of elemental mercury, and you can see each of those here. The highest one is mercury 202. Then you see some HCBr. The highest peak is mercury 202 plus Br79, at least that's our interpretation. And then you see HCBr2 also. When the MS gets bombarded with electrons, then it wants to break apart, and so that's why you see HCBr2, HCBr, and elemental mercury together. But because of the stable isotopes of mercury, it makes it really easy to tell that this is not some column loss or whatever. Like this looks like the stable isotopes of mercury plus the 2 stable isotopes of bromine. The fingerprint is pretty clear, I guess is what I'm trying to say. And then this is just from yesterday, actually. Tanner sent me these images yesterday, and I thought I'd throw them in. So for the first time, we've just been playing with HCBr2, and just Monday we put in the mercury oxide perm tube, and Tanner added mercury bromide, then mercury oxide to the cryotrap, and then desorbed. So we see great separation between mercury bromide and mercury oxide. We've done mercury chloride too in Washington and get less good separation, but still there is a separation. And then you can see because there's not much mercury oxide there, the mass spectra is a little bit uglier, but 218 would be mercury 202 plus oxygen 16. And this got me really excited because I think we've been building mercury oxide permeation tubes since maybe 2006. And the first time we did it, then everyone said we were dumb because mercury oxide the vapor pressure is too low to ever be in the gas phase. If you look at, there's a Schroeder and Munthe paper, and Jerry has a paper where they bring some of that out. And really, the vapor pressures that are published are at least 70 years old, and the methods they use are not reliable. And really, until yesterday, there wasn't a method to measure mercury oxide at all as a compound. And so I think because of the success of mercury oxide permeation tubes, and then this evidence where we know now that that is what's coming out. It's not some other thing that's coming out of the mercury oxide perm tube. We think maybe there's actually mercury oxide in ambient air in the gas phase. So the perm tube is at 100 C, the rest of the system's at 200 C, so that's different than being in ambient temperatures in the gas phase, but it at least is possible. Mercury oxide looks like it can exist. So I guess I'm excited about that because it validates what we did a long time ago and are still doing. And then also, hopefully this machine is opening up kind of a new world of opportunity for understanding mercury in the atmosphere and what might be there. Instead of speculation, we can actually see what's there. I'm not going to talk about the details of what column we're using and that kind of stuff. We can talk about that later. I think I'm probably almost out of time anyway. Am I okay?
We have 6 minutes.
Okay, wow, great. Okay, so I wanted to talk about worries, and one of them Jerry and I talked about yesterday afternoon. So where we're at on this is it's working better than we expected. for permeated compounds. Chaoyan and others, I can't remember who did it, somebody did nylon membranes, loaded them with mercury bromide. They're in our lab now. On Tuesday, we'll do the first test of lab sample desorption instead of just running from the perm tube. And so there might be problems there. And then the next step is, can we do it in ambient air? And so the first question is, what about chemical transformation / decomposition during ambient air collection? We know that's a problem with the KCl denuder. We know it's a problem using quartz wool to collect oxidized mercury. So it probably will be a problem for us too. It's one I anticipate at least. And I forgot to mention, but we're not 100% clear on quantitation on the system yet. So because we really built the pyrolyzer about 3 weeks ago and are not 100% satisfied, but the amount of HCBr2 we're injecting to get the peak that you saw is in the neighborhood of 10 to 100 picograms of mass. So not picograms per cubic meter, just picograms. And so if you have ambient air with 10 picograms per cubic meter, and your detection limit is 10 picograms, then you have to collect a cubic meter, 1,000 liters of air. And probably more than that so you can get a clear sample. And so you have to suck a lot of air through whatever our collection surface is, and that makes more opportunity for this. And it's a problem we'll have to deal with when it comes. The hope is that we can use, like the field mercury calibrator I talked about in the beginning, to add compounds that are similar to or what are in ambient air and do controlled tests of, okay, this is what is in ambient air, this is what it looks like when it comes out. So if that's a problem, hopefully we can design some experiments to address it. The one that I always worry about is, what if what's in ambient air is something we don't even know about yet, or something that's too reactive to make it through our GCMS system? So yeah, the TechRAN system or whatever can see it, but our GCMS system never can, even though it can measure other things. And then we're dead in the water, and NSF won't give us any more funding, I guess. So I don't know how to solve that one. But that's something we worry about. And then also, I think particularly with semi-volatile organics that are physically similar to oxidized mercury, it could be there's some interference. So by physically similar, I mean similar vapor pressure. So they get stuck on the same collection surface, get stuck in the cryotrap, and then just muddy up our ugly, make our signal ugly in our chromatogram and mass spectra. And hopefully we can get around that. One thing that we are doing already is we only look from about mass of 195 to about 400. So most potential contaminants are below a mass of 195. That's a nice thing about mercury because it's so heavy. And so that helps, but there could be other things that we're not seeing. Maybe we need to look down there to see if there's junk that we need to watch out for in other ways. And then we have to sample probably a boatload of ambient air to overcome detection limits. So 1 liter a minute will take a really long time to collect enough sample, but there's ways to get over that too. With a multi-channel denuder that can suck 10 or 100 liters a minute, then we could do pretty quick samples in that way. So that's where we are and where we have to go next. I'm excited about it. I think that it's kind of hopefully putting us to a next stage of understanding. So I think that's all that I have. So that's our funding from the National Science Foundation. Again, thanks to May and her team for their collaborative support. So thank you.
So the challenge for everyone here, even this system, is what do you use as a collection surface? What do you coat it with, and how do you separate the particles? I mean, that's really the bottom line for everything, right?
It is, and I think that's the biggest. I used to think that GCMS was the biggest challenge, but it's turned out to be a lot easier than we expected. The email that Tanner sent me with the stuff about mercury oxide was titled Magic, because I said it's probably going to take us forever to figure out how to do this, but maybe magic will happen and it will work the first time. And so that has worked a lot better than we anticipated. But I think that is the big challenge. There's one good thing about this system. I really think the primary purpose is identification, not quantification. We're shooting for both. But if we can identify what's in the atmosphere, even if it's crummy and we're only getting part of it and there's some chemical transformation, if we can, it will still hopefully get us there, at least eventually. And so that's a good thing to think about. Also, I think we have some good ideas. So the nylon surface that May has been using, or her group has been using for a while now, I think is pretty promising. And we have a couple other ideas too. And one that I always talk about, and you guys are probably getting sick of me talking about, is so the chromatographic column is polydimethylsiloxane, which is just like a BP1 or DP1 regular column that separates by boiling point. And for persistent organic pollutants, then that's what is used usually to collect them from the atmosphere. And I should have mentioned, I guess Helen and I were talking about it, really the idea of this system was stolen from persistent organic pollutant systems because oxidized mercury compounds are physically similar. I mean, in their physical properties, not in their chemical properties. And so the nice thing about about polydimethylsiloxane is it's basically a liquid. And so oxidized mercury compounds can dissolve in it, and oxidants and water don't like polydimethylsiloxane. So they'll be inside polydimethylsiloxane, shielded from the atmosphere. Things that don't like to be inside of it just pass right through a denuder, for example. And so by stealing what other people have done for other compounds, then hopefully we can get farther than just like, okay, here's 1,000 denuder options and let's test them all. So I think there are possibilities, I guess is what I'm saying. But it may be a long road. We may get lucky.
You're saying coat the denuder with polydimethylsiloxane.
Exactly, yeah.
Which is a solid.
It's not a solid. It's a liquid with very, very, very high viscosity. And then you coat it onto the wall, and then you use cross-bonding to make it stay on the wall. And people already do that, and there's commercial companies that can do that. And maybe we can do it if we're really smart.
Yeah. we have another question, sir.
Yeah, so I have a question. One of the properties of mercury is that it forms a very stable complex with methyl, with organocompounds. Have you guys tried maybe forming a complex with organic compounds that GC is able to kind of dissolve it? Because the problem with methyl or with any other organic compounds is that it might really give you like a very scattered signal in the mass spec. So are you just trying with mercury oxide, like very simple, just, small compounds instead of something very complex, because air might contain also some organic compounds inside?
Yeah, that's a good idea. So right now, I think that we think mercury oxide compounds are simple inorganic compounds, but that may not be the case. And we've also, back in the University of Washington days with this system, then we talked about, do we need to basically derivatize the oxidized mercury in order to make it be able to pass through a GC. The problem with that is because we have really low confidence that we know what's in the air. And so if we're derivatizing it or adding methyl groups or whatever, then it's not what it used to be, and then we can't be certain what it used to be when we look at it in the MS. But maybe what we find is that what's in the air, like my last worry, is organic, and it's different than what we said. It's a possibility. And if so, maybe that's good, because then maybe that helps it in the GC system. But we'll just have to wait and see, I guess, what's in the ambient air, which we hopefully will get to.
Okay.